Hello, this is Yanxie. In Lab 5, we are collecting observational data of a magnet falling through a conductive tube of aluminum foil. We then model the magnet-tube interaction computationally and compare our computational predictions with observed data. Some fundamental principles involved in this lab include Faraday's law, Biot-Savart law, Newton's second law, and Newton's third law. My observed time for the falling magnet is 1.174 seconds, while my simulated time is 1.156 seconds. For this lab, I utilized a roll of aluminum foil with a length of 0.38 meters, a radius of 0.02 meters, and a width of 0.008 meters. We cannot use a ferrous tube such as a steel pipe because it contains iron and is thus magnetic. I've measured the mass of my magnet to be 0.022 kilograms and the dipole moment to be 2.31328 am squared. The average time it takes for the magnet to fall through the entire length of the tube is 1.174 seconds. Compared to a magnet falling in free space, the time it takes for the magnet to fall through a tube is much slower due to an increasing magnetic flux in the tube. The first segment of code comprises the geometry of my tube. The second segment includes the properties of my magnet. The last segment is a function that calculates the magnetic field of the bar magnet. Here, Biot-Savart law is applied. In this slide, the first function calculates the flux dt through each ring due to the falling magnet with the application of Faraday's law. The following line of code calculates the gravitational force on the magnet using Newton's law of gravitation. On the top, we have a line that calculates the current in the ring. In the middle, we calculate the magnetic field at each ring and the force exerted on the falling magnet by the tube of rings using Newton's third law. Finally, we calculate the net force on the magnet and update the magnet's velocity and position using Newton's second law. The exact output of my simulation can be found after clicking the link to my GlowScript page. Here, I've pasted the velocity versus time graph and copied the simulated time in the tube, which is 1.156 seconds. Now moving on to the questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. While blue corresponds to counterclockwise current, red corresponds to clockwise current as viewed from above. When I flip the magnet around, the system would exhibit the same motion. The total time in tube of my real-world system is pretty close to that of my computational system. However, the computational system can be made more accurate if we take into account for air and conductivity resistance. The shape of the velocity versus time plot quickly becomes a horizontal line, indicating that a net force of 0 is acting on the bar magnet. If the resistivity of the conductor were reduced as close as possible to 0, the magnet would fall slower due to increased magnetic force and current, according to Ohm's law. If holes or slots were cut into the tube, the ring currents in my model will be smaller as a result of increased resistance. And that concludes my presentation. Thank you.